All right. Oh, okay. So what we had was we had the Ka equation and the Kb equation for. We did dihydrogen phosphate. All right. Thanks. So we had these two equations up. Did we try a whole bunch of other equations? No. We just got to this point. All right. All right. This is an amphoteric species. So there's a Ka here and a Kb here. And so the question is how can we solve this? Let's say we're interested in the pH, the hydronium ion concentration. What a lot of people do is, if I ask for the pH of this salt solution, they'll just do the Ka and ignore the Kb. Is that an acceptable thing to do? Well, unless one of these is very small, we can't ignore it. And neither of these is very small, literally very small, i.e. no number. We have numbers for both of these. And so if we generate some hydronium, we're also generating some hydroxide. So I'll tell you, most errors are people just do the Ka alone. The second error is somebody will do the Ka, figure out the hydronium, and then they'll do the Kb, figure out the hydroxide, and subtract the two. They'll say, okay, that amount of hydroxide is going to neutralize this amount of hydronium, and then figure out the pH. That's wrong too, because that means the hydroxide goes down to zero. It's never going to go down to zero because of water. And so the only way to solve this is we have to solve this. Can we do it stepwise? No, we can't do it stepwise. The only way we can solve it, I guess we could add it, but adding it doesn't quite work because the hydronium and the hydroxide are they aren't going to be tied together correctly. The hydronium and hydroxide have to satisfy the Kw relationship. And so the only way to solve this is simultaneous. We need a hydronium concentration here and a hydroxide concentration here that satisfies Kw. And so what we need to have are these three equilibria are connected by Kw, therefore we have to solve this simultaneous. Ka, Kb, and Kw. And so that means this is a tough problem to solve, right? But we'll see later. We're gonna come back to this later. All right. So what you need to do is you need to recognize that if you have an amphoteric salt, amphoteric salts are tough because that means you have to do simultaneous Ka, Kb, and Kw. And so something that's so simple, it looks so simple, sodium dihydrogen phosphate in water isn't so simple. Whereas something like sodium phosphate is simple. Sodium phosphate is simple because that's only a base, and we did sodium phosphate. Did we do sodium phosphate? Is that correct? Where we did Kb1, Kb2, Kb3, and Kw stepwise. Or if we had phosphoric acid is simple too because that's just an acid. And if we had phosphoric acid, the triprotic acid, we do Ka1, Ka2, Ka3, and Kw. But when we have an amphoteric species, it's not so easy. Sometimes it's easy, like hydroxide. Hydroxide is amphoteric, right? But we don't worry about the Ka for hydroxide because Ka for hydroxide is literally very small. You don't even have a number for it. It's just very small, which means that you aren't going to deal with it. Okay, this was the enteric. All right, so we are going to look at something like this next. What if we had something like sodium dihydrogen phosphate and sodium monohydrogen phosphate? You know, now it seems like this is going to be tough as well, right? This seems like it's going to be tough because we just saw 1 amphoteric is going to give us trouble. Now 2 amphoterics in solution are going to be double the trouble, right? But it turns out that, you know, even though both of these are amphoterics, you know, this one, the sodium ions are neutral, so we'll just ignore the sodiums for now. And so we're looking at these 2 amphoterics, dihydrogen phosphate and monohydrogen phosphate. And so this one looks tough as well, but this one is not tough. This one is easier. It's easier because of this. Dihydrogen phosphate will no longer behave as an amphoteric. You know, dihydrogen phosphate will behave as the acid. Because here, you know, dihydrogen phosphate can act as an acid or base. Monohydrogen phosphate can act as an acid or base, and water can act as an acid or base. And out of these 3, which one is the strongest acid? Well, it turns out dihydrogen phosphate will be the strongest acid present. And which one's the strongest base present? The strongest base present will be water or monohydrogen phosphate. So we look it up on the chart, and we'll see that monohydrogen phosphate is actually stronger than water, just based on the chart position. And so we got and so what happens is this takes out the amphoteric character, because if monohydrogen phosphate were going to try to act as an acid, it's going to be overpowered. There's a better acid present. And so the base is preferentially going to attack this. And the same thing, if dihydrogen phosphate tries to act as a base, well, it's a much weaker base than monohydrogen phosphate, so it's not going to react as a base. And so in this combination defines the roles of each of these species. So this is only going to act as the acid, and this is only going to act as the base. Now what do we do? Well, we have an acid-base mixture. We have an acid-base mixture. How do we handle that? Well, you know, basically we've been dealing with acid-base mixtures all along. In chapter 16, we've been dealing with acid-base mixtures, right? And what we did was we reacted the acid plus water being the base, or the base plus water being the acid in that case. And so we do the same thing. You know, we just take the strongest acid present and react it with the strongest base present. And so in this particular case, we rather than reacting it with water, we're going to react it with the stronger. So we have a stronger acid present, H2, and we have a stronger base than water. So water is just going to spectate in this at this point. You know, later on, water has to be tied in there. And so here we have our acid, and we have our base. And this is going to produce what? No, it's hydronium comes from acid hydrolysis, you know, acid plus water. But in this case, we don't have acid plus water. We have to transfer a proton from the acid to the base. And so the difference between this and chapter 16 is we would have produced hydronium immediately, but in this case we aren't. In this case we're going to produce yeah, okay, you're right. So we're going to have monohydrogen phosphate. This loses a proton, this gains a proton, and dihydrogen phosphate. And then we say, oh, wait a minute, that's the same as this, right? If it's the same as that, then we're done. Are we done? This is no reaction. No reaction. Well, this didn't lead to a unique product. So what we do is we look for the next strongest acid or the next strongest base. And so this didn't lead to a product, but looking for the next strongest, we would have something like this. We'd have, let's go with H2PO4 minus. What's the next strongest base? Well, this base didn't yield any unique product, so the next strongest base present would be water. And so in this case, we're going to have H2PO4 minus plus H2O liquid. This is going to give us hydronium and monohydrogen phosphate. But we recognize this one. This one is Ka, right? Acid plus water. So we know that this one, we know how to deal with it. But in the previous chapter, that's all we had to deal with. Now we got this base in here as well, and we have to deal with that. And so how do we deal with the base? Well, the base is going to react with the next strongest acid. And the next strongest acid would be, again, it would be water. You know, since the strongest acid didn't yield anything, we'll go with the next strongest acid and see if that collision yields something unique. And we'll see. And so this is going to produce H2PO4 minus plus hydroxide. We look at this, oh, that's just a Kb. Uh-oh, I've seen this before. We've seen the Ka and the Kb, right? And it turned out to be quite a challenging problem to solve because we had to do simultaneous Ka, Kb, and Kw. Do we have to do the same thing here? We have to do simultaneous Ka, Kb, and Kw. So look at this one carefully and compare it to the last one and see, is the method going to be the same? Or do you see something special about this one that's different than the last one? Well, it turns out there is something special about this one. I don't know if your eyes are trained to see this quite yet. So,
Just that the products of the acid is the same as the base.
yeah, you know, we saw something very similar to this not so long ago. And what did we say about these two equilibria? Well, not this specifically, but we saw something very similar to this. Very, very, very similar to this. Yesterday or day before, lecture before. I think it was yesterday.
The same reaction is represented in different directions.
Not well in different directions. Yeah, about I actually said it a little bit differently. I guess you could say that same reaction. These represent the exact same equilibria, right?
Yeah.
The equilibria between H2PO4 and HPO4. This is the same. These two are the same. The only difference is one expresses it in terms of exactly. One's pH, the other's POH. And so we wouldn't do these simultaneously because it would be weird because we'd be repeating the same thing. We do one or the other, right? One or the other. Normally you would do the one with the larger K value. You know, you just pick it, but no, we're gonna probably stick with Ka because it's more convenient. Even though, let's say Kb were bigger, the only thing that might trip you up is the simplifying assumption might, you know, because if we do Ka and it's a basic, you know, Kb is bigger, then hydroxide is a dominant species, then the simplifying assumption is going to fail for Ka, but we have to remember we're using Ka, not Kb, for a basic solution, and it's not exactly right, but it'll give us the same answer because they're tied together by Kw. In fact, we could have saved ourselves a lot of time had we just recognized this combination. This combination is called a conjugate. Yeah, this is a conjugate. This is a weak acid, weak base, and they're conjugates of each other, and I could have saved a heck of a lot of work if I just went straight to the Henderson-Hasselbalch equation. I didn't have to do all this stuff had I just recognized, well, maybe you did recognize it earlier, but and so this is an HH buffer, and so just didn't have to do that. But you know, even if we did this, because what I'm showing you here is this is the general method to solve this, and the general method is you have to recognize these types of things and how you'd solve it. And so we could have continued. In this case, it would have been perfectly fine just to do the Ka. In the last case, it's not acceptable to do the Ka. Right? But you know, some people will do the Ka for every case, and that's wrong. You know, just the Ka. And so here we'll just use the Henderson-Hasselbalch equation, HH equation. And the HH equation is that the pH is going to equal the pKa for the acid. The acid is going to be the H2PO4 minus, plus the log of the base. The base is going to be HPO4 2 minus over the acid, H2PO4 minus. So it's base to acid ratio. And so we just plug in this is given, we plug in the concentrations, whatever concentrations we have. And the great thing about this is if the simplifying assumption holds, we don't have to plug in the equilibrium concentrations, we plug in the initial concentrations, making the calculation very quick and easy. And so if you recognize that this is a Henderson-Hasselbalch buffer right off, then you can save a lot of time in the calculation. But the situation is, people once they know the Henderson-Hasselbalch, they try to use the Henderson-Hasselbalch for all acid-base mixtures. Does it work for all acid-base mixtures? You know, and so what they do is they get any acid-base mixture. Like for example, I'll give them sodium hydroxide and HCl. And they'll try to use the Henderson-Hasselbalch because they know it's the base to acid. So they'll plug in the sodium hydroxide concentration here and HCl concentration and try to calculate it. I've seen that so many times. That's not going to work because it has to be weak acid, weak base, and they have to be conjugates of each other. And so it's restricted. Well, we can have... Well, what if we have a weak acid, weak base combination that aren't conjugates of each other? What do we do then? And so let's go with another weak acid, weak base combination. I'm going to go with acetic acid. I'm going to use the abbreviation for acetic acid. You know, HA is the general abbreviation. A just stands for any generic anion. You know, AC is for specific anion. It's for acetate. And so if we have acetic acid, and let's go with 0.100 molar acetic acid, and I'm going to keep this simple, 0.100 molar ammonia. So we have acetic acid and ammonia. And so this is a weak acid, weak base combination. But they are not conjugates of each other. And so what do we do? Well, normally when we have an acid and base, we do a neutralization type reaction, right? And so in other words, this chapter is full of acid-base mixtures. In acid-base mixtures, we take the strongest acid present and react it with the strongest base. And did I already write that down? And so the strategy for chapter 17 is strongest acid plus strongest base. And then just repeat. I'll show you what I mean by repeat. Now, or we do the biggest K. You know, sometimes we'll do step I, you know, where we'll ionize the species. So in this mixture, we have acetic acid, ammonia, and water. So what's the strongest acid present? Acetic acid or water? Actually, ammonia is amphoteric. Did you know ammonia is amphoteric? Ammonia is amphoteric, but the Ka for ammonia is very small, literally, and so it's negligible, so we ignore it. And so acetic acid or water, which one's stronger? Acetic acid. So the strongest acid present is acetic acid. What's the strongest base present? Ammonia. And so what do we get? Well, we get an acid-base reaction, Bronsted. And so this Bronsted acid-base reaction is going to produce what? It's going to produce acetate and ammonium. Acetate and ammonium. But, you know, what is the K value for this? Yeah, we don't have the K value for this. It's not in the book. It's not on the chart, but did we already use Hess's type law to solve for K value? We talked. Did we do it? All right, let's do it here. Let's what we're going to do is we're going to use some chapter 15 methods. And so what we're going to do is we're going to try to add up equations that we know the K values for to get the K value for this. And so what are the equations that we can add up? Well, for acetic acid, what's the only equation that you pretty much know that you have the K value for? Ka. And so we have the Ka value. That's going to be here. This is K for acetic acid. We looked that up. That's 1.8 times 10 to the minus 5. And then we need the Kb value for this. Now the Kb value, this is going to be weird, but the Kb value is 1.8 times 10 to the minus 5. They aren't the same. They're only the same to 2 sig figs. They're actually different. So this is a unique coincidence. They aren't related in any sense. But essentially, as strong as acetic acid is an acid, it'll be equal to the strength of ammonia as a base. And so they're just opposite, equal, and kind of equal, not exactly equal, because the 3 sig figs, I don't think they match. But you can think of them as kind of equal and opposite. Maybe if they're equal and opposite, they cancel each other out, and pH is just 0. But let's continue here. I mean, pH not 0, 7. If we add these two equations up, what do we get? We get acetic acid plus ammonia plus 2 waters. This is going to produce hydronium plus acetate plus ammonium plus hydroxide. It's getting a little closer because, I mean, we have acetic acid and ammonia, we have acetate and ammonium, but we also have hydronium and hydroxide, which we don't want, and water, which we don't want. Is there a way to get rid of those?
Add KW to it in reverse.
Yeah, if I just reverse KW, so I'll go hydronium plus hydroxide, this is going to produce 2 waters. And so that's the reverse of the KW. And so far what I have is I have Ka times Kb, but these aren't conjugates. Let me see, actually, let's look at this here. Write this down. So I have the Ka for acetic acid times the Kb for ammonium. Hey, isn't Ka times Kb Kw? No. Ka and Kb, Ka times Kb for conjugate pairs is Kw. But this Ka and Kb are not for conjugate pairs, so this does not equal Kw. This is going to be the K value for this. This is equal to the K for that sum. And then this is the reverse of Kw, so we just invert that. And so now when we add these up, I have acetic acid plus ammonia, and the hydroniums cancel, the hydroxide cancels, and the 2 waters cancel. And so what I'll be left with is acetic acid plus ammonium yields acetate and ammonium. The K for this reaction is going to equal Ka times Kb divided by Kw. Let's figure out what that K value is here. Actually, I got the calculator here. Look at 1.8 times 10 to the minus 5 squared. Divided by 1 times 10 to the negative 14. That give me I get 3.24 times 10 to the 10 to the 6. Is that what you guys got? No? 10 to the 4th? Screw that up. But yeah, I'm not very familiar with this calculator. 10 to the 4th? Is that what other people got?
Yes.
All right, 10 to the 4th it is. All right, so we have the K value for this. It's 3.24 times 10 to the 4th, which means, you know, it makes sense because we're going from stronger acid to weaker acid, right? But this is not a complete reaction. This is kind of an equilibrium type situation. And so what we want to do is we want to figure out, let's try to figure out what the pH of this particular mixture will be. And so what we're going to have is we're going to have 0.100 molar, 0.100 molar, and 0 molar, and 0 molar. Okay, what would you do next? Oh, it would go to the right, so it would be minus x, plus x, plus x. Is that what you would do? Okay, any other?
Should you reset this?
I would reset this. I mean, this is 10 to the 4th, so I'd reset it to the right. And so let's go ahead and reset it. Tell me what the reset. Now, the reset is you got to put in this minus y, plus y, plus y. You know, if you do that, then you see, I mean, this is easy because it's all 1 to 1 to 1 to 1, but sometimes it's not all 1 to 1 to 1. And this is easy because it's stoichiometric. Sometimes it's not stoichiometric. Sometimes there's a limiting reagent involved. Right? And so there are some errors on the last test with the limiting reagent. But anyway, this is going to go to 0, 0, 0.100, 0.100. And so now the change is going to be reversed. So it's going to be plus x, minus x, minus x. And so at equilibrium, we're going to have x, 0.100, minus x, 0.100, minus x. And then we could solve this for x. Let's do that. Solving for this for x, K is going to be the acetate concentration times the ammonium concentration divided by the acetic acid concentration and the ammonia concentration. And so I'm going to get 0.100 minus x squared, quantity squared on the top, and then x squared on the bottom. Well, this one turns out to be a quadratic, but it's an easier quadratic because we could just take the square root of both sides. We take the square root of both sides and then solve for x. Or we could use the SA. Maybe we should have just used the SA. Let's try the SA. But this one was easy. The quadratic wasn't required, so that's why I figured, well, we can get a more accurate answer if we don't use the SA, and the math is not terribly difficult. But the SA should have worked fine if we reset it. If we didn't reset it, then the SA definitely would not have worked. So does somebody have X?
0, 0, 0, 3 zeros.
Triple zero five, and then zeros after that?
Which is 5 repeating.
Oh, 5. Okay. 5, 5, 5. All right. So we have 0.00055 molar, 0.00055 molar, and then we subtract this. This is going to be 0.099445. Is that right?
Yes.
445 and 0.099445. All right, now we should double check our K to make sure. So let's check the K value and see if it worked out all right or not. It works? Okay, good. Okay. So if it's okay, then we're good. But what do we do next? Are we done? It looks like we're done. We reacted the acid and the base, but
You wanted the pH.
we want the pH. How am I going to calculate the pH?
Do you have to react before
Yeah, well, we generated some. We have these species now. And these species are going to hydrolyze water, right? And so let's take a look. Well, here we have acetate. We'll start off with the higher concentrations because this is going to be more significant, maybe acetate and ammonium. Or should we start with larger Ks? You know, even though the concentration's smaller here, the K values are going to be a lot less. So if we look at acetic acid has a Ka of 1.8 times 10 to the minus 5. We'll just look at the K values in general. This would be Ka. Ammonia, 1.8 times 10 to the minus 5. That would be a Kb. Acetate, what would the K, acetate's a base, right? And so the Kb for acetate is equal to Kw over the Ka for what acid? The conjugate acid of acetate, which is acetic acid, HAC. And so this is 1.0 times 10 to the minus 5 divided by 1.8 times 10 to the minus 14. Oops. 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, which gives us, what is it, 5.55? Is that right? Times 10 to the minus 10? Yes?
Yes. Yes.
Okay, great. And then we have ammonium. Ammonium is going to have a Ka value. The Ka value is going to be Kw divided by the Kb for what base? The NH3. Good. And so, well, that's 1 point. You know what? The numbers are the same, right? And so this is going to be 5.55 times 10 to the minus 10. Now, what should we do? Well, normally we do the biggest K, right? Biggest K. But look at the difference in concept. Well, not hugely different. We'll just do the biggest K. Even though these ones have, these are smaller Ks, but they have higher concentration. And so we'll do the biggest K. So we have a choice because they're kind of tied. And so which one should we do? Should we do Ka for acetic acid or Kb for ammonia? Well, if they're tied, I guess it doesn't really matter, so we'll just pick one. We'll do Ka for acetic acid. So we're going to say we generated 0.000555 acetic acid. So acetic acid is going to hydrolyze water to produce hydronium and acetate. We are Ka. And then we'll try to do this stepwise, working down to the smaller Ks. Should we do it that way? And so we'll do the ice table for this. And then we'll go down to ammonia. But when we look at ammonia, ammonia plus water yields ammonium and hydroxide. This is Kb. Do the ice table for that. Do we carry down anything here? Actually, it looks like these two are separate, right? We don't carry down anything from step 1 to step 2, do we? Yeah, I'll go from there in a minute. We're just looking at the strategy right now. Okay, then let's go to acetate. Acetate plus water. This is going to yield acetic acid plus hydroxide. This is a Kb. Do the ice table for that. And then we have ammonium. Ammonium plus water. This is going to give us hydronium and ammonia. It's Ka. Done. Do the ice table. So should we do these 4 ice tables here? Maybe we can combine them. But look at the equilibria carefully, and what do you notice? Yeah, you look at this first, the top 2 here. What do you notice when you look at the top 2?
It's the same equilibrium.
It's the same equilibrium. We're just repeating ourselves, right? To do the top 2, both would be, yeah, redundant. So we don't need to do this one here. Look at the bottom 2. What do you see?
It would be redundant.
That would be redundant as well. We don't need this. All right, so we just need to do these, right? And so when we do this, let's go with acetic acid was the 0.000555, and the acetate here was a 0.099445. Is that right? But you know, water's blank, hydronium's 0. But you know what? There's another strategy for resetting. The other strategy for resetting is to get more zeros in your initial, because that means fewer binomials. Because now, if we do the change, this is going to be minus x, x, x. And so we're going to get 2 binomials here. You know, the 0.00555 minus x, and the 0.099445 plus x. That's 2 binomials. I don't like, fewer binomials is better, right? And so why don't we just reset this? Can we reset this one to the left? Impossible. We can't reset this one to the left because the limiting reagent is already hydronium, and that's been completely consumed. There's nothing more to react. The only way we can do this is to reset it to the, we could reset it to the right. Set it to the right. And the same thing here. Reset it to the right. But in the in the end, now this is kind of a long journey. A long journey trying different things, writing out all the equilibria to come to this. The final conclusion here is this. In this particular example, we have the weak acid, acetic acid, and the weak base, ammonia. And what's going to result in this combination is this. Basically, we cannot solve these separately because one produces hydronium, the other produces hydroxide, and they cannot be independent of one another. The hydronium and hydroxide must be tied together. And so the only way to solve this system of equations is simultaneous. Simultaneous with Kw. And so when we have a weak acid, weak base, one, this is a buffer, but it's not a Henderson-Hasselbalch buffer. Because what's going to happen is the acid and the base will coexist at equilibrium. And so it is a buffer. And two, we have to solve this simultaneous with Kw. What equations do we solve simultaneous? We solve the Ka and the Kb. And so if we already know this in advance, the way we set this up is we would have HAC at 0.100 molar plus water, H2O liquid. This is going to go to hydronium and acetate. This would be 0. Actually, this is simultaneous. We have to have some concentration of hydronium that fits all these. Then we're going to have the ammonia plus water going to ammonium and hydroxide. And then we're going to have Kw. So this would be 0.100 as well. So we have to solve this simultaneously. And then we can get the pH of this mixture. And so if it's a Henderson-Hasselbalch buffer, which is weak acid, weak base, conjugate pairs, then it's easy because they're conjugates of one another. And so the math and everything else is easier. But if you have a weak acid, weak base that are not conjugate pairs, then it's tough. This is a very tough problem because it's simultaneous. Are we actually going to solve it even though it seems simple? You take a weak acid, weak base, you try to neutralize them, it seems like a simple calculation, but it's not. This is a very difficult calculation. And so this one we don't solve, we just recognize that it's simultaneous. Okay. Now, those are the tough ones. Now we're going to get to some easier ones, but before we get to the easier ones, I just want to talk about Henderson-Hasselbalch buffers a little bit more. And so it's nice when we have a Henderson-Hasselbalch buffer, and we can do a lot more with Henderson-Hasselbalch buffers. Henderson-Hasselbalch buffers, you know, the most versatile are when the acid and the base are in equal amounts or equal concentrations. And so we have something called the ideal pH. Ideal pH is when the base concentration equals the acid concentration. And the reason it's ideal is because this is the most versatile. We have something called capacity. And the capacity is the ability to neutralize added acids and added bases, like strong acid HCl or strong base sodium hydroxide. Did I already talk about buffers a little bit, like adding HCl to a buffer? I think I did, didn't I? Or adding sodium hydroxide to a buffer. One of the components will neutralize And so this is most versatile because they have equal capacity to neutralize. Both added acids and added bases. So if we have something like this, let's say the acid concentration were 0.100 molar, but the base concentration were 0.0000100 molar. Then we have dramatically different capacities here. And so here we have decent capacity here, and so this would be higher capacity. But here we have very low capacity. And so getting to a specific example, let's take a look at acetic acid. Let's say the acetic acid were 0.100 molar, and then we have sodium acetate. Sodium acetate were quadruple zero, 100 molar. Then what's going to happen is if I add sodium hydroxide to this mixture, and this is going to be a stable mixture of both, I'm going to have acetic acid and acetate in here. The sodiums are spectators, essentially. And so we'll just look at this. And so if I add sodium hydroxide, I have some decent capacity to neutralize that because the acetic acid will neutralize the sodium hydroxide. But if on the other hand I add HCl, I can't add that much HCl before I completely deplete the acetate. There isn't much acetate, so it's going to quickly run out. And so the HCl, I have very limited capacity to neutralize that. And so this is what we mean by capacity. And so the higher the concentration, the higher the capacity. Also, the higher the concentration, the more expensive the buffer is going to be because it's going to cost more for more materials. All right, we aren't fixed at the ideal pH though. The pH of buffers can be adjusted. We just try to keep the range, to the ideal pH plus or minus 1. The reason for this is because we don't want a lopsided buffer. And so, if we recall, the pH of a Henderson-Hasselbalch buffer is equal to the pKa plus the log of the base to acid ratio. And so what this is going to do is this. If we have, let's say, 10 to 1 base to acid ratio, we'll just call it B. Okay. And so if we have a 10 to 1 base to acid ratio, then the pH is equal to the pKa plus the log of 10 over 1. That would be the concentration ratio. This is just the ratio, not the exact concentration. So the log, a base 10 of 10 is 1. And so this would be the pKa plus 1. If we have a 1-to-1, then the pH is equal to the pKa plus the log base 10 of 1-to-1, which is 1, which is just equal to the pKa. If we have a 1 to 10 ratio, and so we have 10 times more acid, the pH is going to equal the pKa plus the log of 1/10, which is just pKa minus 1. And so what we're trying to do is we're trying to keep it within a 10 to 1 or a 1 to 10 ratio. And so this is what we'll call the buffer region. A 10 to 1 to 1 to 10 ratio of base to acid. Okay, if we go outside this, you know, let's say we get to 101. If we're at 101, then the pH is equal to the pKa plus 2. You know, and so here we're going to have a large amount of base, but not much acid, because we can't make a 100 molar solution. So if we made this at 1 molar or 0.1 molar, this would be 0.001 molar. That's fine. Or if we go outside 1 to 100, the pH is equal to the pKa minus 2. And so this would be outside. And the reason it's outside is because it's a lopsided buffer. You know, we have a huge amount of one component, but very little of the other component. And so it's not a very versatile buffer. Well, it'd still work, but what would happen is you'd overwhelm one of those. And so the region, the buffer region, this is ideal. You know, within the 10 to 1 to 1 to 10 ratio, we still have significant amounts of both acid and base present. And so that means we can try to make buffers. And so let's do making buffers next. Let's say we want a pH 7.00 buffer. Okay, how would one make this? So the first step is you want to find a acid. So we want a weak acid with pKa around 7. And so what acids would have a pKa of around 7? So we'll have to take a look at the book. But before we do that, we'll take a break and then we'll continue this.